Merry day after Christmas. And what better thing to talk about the day after Christmas than rust? Because all those presents you just got, they're going to go the way of the dodo. Why, I remember when I was a boy, I got a yellow Tonka dump truck for Christmas. And eventually that happened to it. Rust. What is rust? It was oxidized. The name, the idea of oxidation comes from the fact that these sorts of reactions were first noticed when metals corroded or rusted in the presence of oxygen. And so the old chemist used to say it's been oxidized, right? So what's really going on, though, when we talk about oxidation? This is the third kind of reaction, by the way, we're talking about in this chapter. We're following Brown, LeMay, Burston, and Murphy's Chemistry, the Central Science. We are in chapter 4, aqueous solutions, what happens in watery kinds of circumstances. We've talked about precipitation reactions. You take solution A, solution B, you put it together, and plop, oh, there's something there that wasn't there before. It's a precipitate. We talked about acid-base reactions. We've got something soury, acid, bittery, basic. Mix them together, and it tastes just right. It's balanced. Trust the force, Luke. Okay, this video is on oxidation reduction reactions. What's happening in an oxidation reaction? Well, something is losing electrons. Again, day after Christmas, think of it as an electron gift exchange, except it's only going one direction. I've got you some electrons for, in your elephant gift. Look in your stocking. One person is giving away electrons, another person is getting electrons. So that's what's happening with oxidation. Something is losing electrons, something is gaining electrons. Now we say that the thing that is losing electrons is being oxidized. My old chemistry teacher, Mr. Atkinson, used to say ox loss. Oxygen means loss of electrons. I don't know whether he said anything about losing an ox. Maybe he did. He was a funny guy. But ox loss, when something is being oxidized, it is losing an electron, also known as an ox. Okay, so the thing being oxidized is losing electrons. Now we say that the thing that is gaining electrons is being reduced, which makes no sense. It probably does make sense, but let's not think about it, right? I think it's just going to confuse us if we try to make sense out of it. Let's not make sense out of it. Let's just memorize it. Ours is not to question why. Ours is just to memorize or die. So ox loss, the thing that's being oxidized is losing electrons. And we say that the thing that's gaining the electrons in the gift exchange is being reduced. Okay, let's give an example. So let's take some solid calcium, which is neutral, it has no charge. And then let's say we've got it in an acid, which has some protons lying around. So we've got hydrogen 1 plus. By the way, when we're talking about a charge, you put the number first. Calcium 2 plus. When you're talking about the charge, you put the number first. Okay, so you got some protons lying around in an acid. And so what's going to happen is the calcium is going to lose its 2 electrons. So calcium is being oxidized because it's loss, ox loss. The calcium is losing. By the way, there's no oxygen in this equation. So calling it oxidized, the old chemists didn't know what they were talking about completely. They knew a little bit of what they were talking about. So oxidation does not require oxygen. Just forget that. Okay, that was a side note. So the calcium is being oxidized because it's losing electrons, right? If something loses negativity, it's becoming more positive, right? So the calcium loses a couple negatives, a couple of electrons, and it becomes more positive. So ox loss of electrons. Where do those 2 electrons go? Why, the hydrogen takes them. Hydrogen goes from being 1 plus to being neutral. And so those 2 electrons go to the hydrogen, and we get bubble, 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 bubble. We get hydrogen gas, which has is at peace. So the hydrogen has gained electrons. It has been reduced. The calcium has lost electrons. It has been oxidized. So we call this a redox reaction. Read from reduced and ox from oxidized. So a redox reaction is an oxidation reduction reaction. Okay, now hopefully it's not been too confusing so far. Let's try to keep it that way. So the thing that is being oxidized is causing the other thing to be reduced. And the thing that is being reduced is causing the other thing to be oxidized. So we might say that the reducing agent, the thing causing the other thing to be reduced, is the thing being oxidized. And the oxidizing agent, the thing that's causing the other thing to be oxidized is being reduced. So it's flipped. The agent is the one doing the thing to the other thing. And so it's experiencing the opposite. So the reducing agent is reducing something, it's being oxidized. The oxidizing agent is oxidizing something, it's being reduced. So it's the agent is flipped. All right. It's an agent that flips. My daughter didn't learn ox loss. She learned oil rig from her teacher, who is Mr. Tippy or Christy. Anyway, Philippi. She had 3 teachers of chemistry. One of them taught her oil rig. Oil rig is oxidation is loss, rig, reduction is gain. Okay, ox loss, reduction is gain. All right, that might help you as well. All right, now, next, let's talk about oxidation numbers. Try to hold it together. We can get through this. So oxidation numbers are a way of kind of keeping track of where the electrons are. This is a electron counter method. We're going to count the electrons and make sure we know where all the electrons are. Do you know where your electrons are? So here are the basic rules for oxidation numbers. So it's a way of keeping track of electrons. It's electron money counters. Okay, so if something is in its elemental form, it's not giving anything away. I got 0. I'm not giving anything away. I got 0. So in elemental form, it's keeping the money. Its oxidation number is 0. If something's in its elemental form, so if you have like silicon with no charge, its oxidation number is 0. If you've got H2, you've got hydrogen gas, its oxidation number is 0. Okay, in elemental form, oxidation number is 0. That's easy enough so far. Now, if you've got an ion which has a charge, its oxidation number is whatever its charge is. Although you flip the way they made it confusing. Why do they do this? So we put the number first with the charge. So we would say fluorine 1 minus if we're talking about the charge. But for oxidation number, we put the charge first. So the oxidation number of fluorine would be -1. Anyway, don't let that bother you. If you don't get that part, you'll survive. But for a monatomic, mono means 1. For a single ion, like hydrogen, which is 1 plus, its oxidation number is +1. Okay. Oxygen tends to be, its oxidation number tends to be -2. Again, notice where the sign is. For oxidation numbers, the sign goes in front. For the charge, the number goes in front. Again, don't worry about it. My brain is full. Don't worry about it. That's the least of your worries. All right. So oxygen tends to be -2. Hydrogen tends to be +1 with nonmetals. Again, if your brain is full, forget that it can be something different. Just remember +1. That's the most important thing to remember with metals. Fluorine, as I said, tends to be -1. That column, column 7, group 7, the halogens be thy names. That tends to be -1 as the oxidation number. Why? Because they tend to take a 1 minus charge. All right, so these are the rules. If you have a neutral compound, so like H2SO4 has no charge as a compound. So all of the oxidation numbers in that, the hydrogen, the sulfur, the oxygen, they all have to add up to 0 if you have a neutral. If you have a neutral compound, all of the oxidation numbers have to add up to 0. Or if you have a charged compound or charged ion, all of the elements have to add up to whatever the charge is. Okay, does that make sense? If not, hopefully these examples will help it make sense. So let's talk about S8, sulfur. What is the oxidation number of S8? Well, is there any charge on S8? Nope. And so it's elementary, my dear sulfur. It's going to have a oxidation number of 0 because there's no charge on it. It's just 0. All right. S8, 0. It's elementary. What about the sulfur in sulfur chloride? Well, we said that since chlorine is a halogen, its oxidation number is going to be -1. We have 2 of those chlorines, so the oxidation number for this last part, the negative part, is going to be -2. That, for it to balance out and equal 0, that means that the oxidation number of the sulfur has to be +2, okay? And so +2 is the oxidation number of the sulfur in sulfur chloride, because the chloride part ends up as -2. What about the sulfur in sodium sulfate? Okay, getting a little hard. This is the hardest on this video. If you got this, you got it. So sodium is an alkali metal in the first column. And so it's going to take a 1+ charge. So we're going to say that oxidation number is +1. There are two of them. So this side, the positive side, the cation side, is going to be +2 for its oxidation number. That means the sulfate sulfate ion, has to be -2 because there's no charge on this. So if this is +2, this has to be -2. Now, here's where it gets a little complicated, because oxygen is in the third to last column, right? It tends to take a 2- charge. So its oxidation number tends to be -2. There are 3 of them, so that's -6. So I've got to get from -6 to a total of -2 here. I think +4 will do the trick. You could have written it out if it was confusing to do in your head. I've got +2 with the sodium, plus whatever the sulfur is, then -6 with the oxygen. That all has to equal 0. Okay, so what number is missing here? I can do a little algebra, and +4 will do the trick. So +2 plus 4 is +6, -6 is 0, right? So +4 is the answer. All right, one last one, and this one isn't as hard. What about hydrogen sulfide? I think it is. So again, hydrogen, very first column, has an oxidation number in this case of +1, but there are 2 of them, +2. So the sulfide has to be -2 because this has no charge. Okay, so that's how oxidation numbers work. Phew. Okay, oxidation of metals. Let's talk a little bit about the oxidation of metals. So there's there are several different kinds of reactions that are oxidation kinds of reactions. One of them, for example, is a combustion reaction. That sounds fun. We'll have to wait for a later chapter. I mean, it's motivation, right? To keep going in chemistry to get to the combustion reaction eventually. The one that we want to talk about in this chapter 4 is what's called a displacement reaction. Now, we had an exchange reaction earlier on. Remember, we had AB plus BC switches around, to be, anyway, they switch swing your partner reaction. A displacement reaction is an A plus BX leads to AX plus B. So I think it's called a displacement reaction because the X is displaced from the B and relocated, in a witness protection plan with the A. So, but you can see that it's a little bit like an exchange reaction, except you don't have a double exchange. It's just a single kind of exchange. That's called a displacement reaction. For example, let's say we've got solid zinc, and we put it in some acid, hydrogen. Notice there's an overlap here. We have both an oxidation reaction and a acid-base reaction. They can overlap sometimes. So we have zinc in an acid. What's going to happen is the hydrogen is going to oxidize the zinc. The zinc is going to be oxidized. It's going to ox loss. The zinc is going to lose electrons. Right now, it's neutral. But here in zinc bromide, it's going to be +2. Okay, so it goes from being 0 to +2. That means it's electron exchange, gift exchange. It's given its electrons away. Where has it given its electrons? Where has it given its electrons? To whom is it given its electrons? It's given its electrons to the hydrogen. So the hydrogen here is a oxidation number of +1, and there are 2 of them. And so what happens is the 2 electrons bring hydrogen to a neutral state. So the zinc is oxidized, it loses electrons. The hydrogen is reduced, it gains electrons. So the zinc is the reducing agent of the hydrogen, and the hydrogen is the oxidizing agent of the zinc. Okay, so this is a displacement reaction. It is an oxidation reduction, a redox reaction. So this is an acid doing it. Here is an example of a salt, nickel nitrate salt, reducing or oxidizing the iron. So here we start with iron, which is neutral. Over here, the iron has become uh, a 2+ in charge, or it's gone from having a oxidation number of 0 to having an oxidation number of +2. So it has lost electrons. It has given its electrons up in the gift exchange. Where did the electrons go? They went to nickel. So here, the oxidation number of nickel is +2, going along with the -2 of the nitrate, right? But the nickel goes from +2 to neutral. It gains 2 electrons. It is reduced. So the nickel is reduced, and then the iron is oxidized. And so we have a displacement. The nitrate is displaced from the nickel to the iron. Okay, so we have 2 different kinds of redox reactions here, one involving an acid, one involving a salt. We want to end this video, you're saying, please end this video, with what's called the activity series. How do you know if this is going to happen? Well, these are ranked, so I put it on one slide, but it starts at the lithium is at the top, then we're going down, 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 and then we'll keep going down, down. Now here, so that I could get it all on one slide, this is going down, 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 down. Okay, so we have lithium at the top of this series and gold at the bottom. So anything above something else can be oxidized by it. So like gold is at the bottom. Gold can oxidize all of these. Gold can cause all of these other ones to lose electrons. It's like you're going to be in this gift exchange whether you want it or not. Gold is the one that makes everybody. Lithium is the one most required to give up its electrons. But magnesium can make lithium give up its electrons. Hydrogen can make lead give up its electrons. See how it works? Chromium can make barium give up its electrons. Barium doesn't want to, but he has to. Gold, you can see that the farther down we get here, we get toward what are called the noble metals. The noble metals don't rust. They don't corrode. Why? They don't oxidize. They're like gold is at the bottom of the chain, which in this case is good. It means that gold, nothing can make gold oxidize. Nothing can make gold give up its electrons. Platinum, only gold can make platinum give up its electrons. But gold can make silver give up its electrons, but silver can make copper give up its electrons. Iron can be oxidized by anything down here, especially, for example, hydrogen. And iron, however, can make magnesium become oxidized. So the higher up on the list, the more easily oxidized it is. The lower on the list, the harder it is to oxidize it, to make it to give up its electrons. Okay, well, that's enough. This has been a video on oxidation reduction reactions.